Good morning everyone, welcome to today's worked exam answer video. Today I'm having a look at an AQA GCSE question covering reversible reactions and the concept of Le Chatelier's principle in how the position of equilibrium will shift when we change concentration and temperature. Whilst this is an AQA question, I know for a fact that this content also comes up in the EdXLI GCSE triple award course, and it comes up in the OCR GCSE as well, and it may come up elsewhere that I'm not aware of, so just make sure that this is definitely something, if you are studying GCSE, that you need to be aware of. So we've got a reversible reaction, and it's one where we've got different coloured ions involved, and we're going to be asked about colour and how the colours can help us to explain how the position of equilibrium might have moved. So on this first page we're looking at changing the concentration of one of the things in our reversible reaction, and then on the back we're thinking about changing the temperature, having a think about why pressure is not affecting the colour of our equilibrium mixture, and then they've thrown in a lovely kind of synoptic question here, whereby they're drawing upon your topic 1 knowledge and how transition metals versus group 1 metals or other metals on the periodic table have different properties. So we'll come back to that a bit later. So first things first, this question is about a reversible reaction. I know that, even if they hadn't told me it, because we have this little arrow here. So rather than it being a full forward facing arrow, we have the half arrow pointing forwards and half arrow pointing backwards, and that tells us that this reaction can go both ways. Okay, so we can see that we've got solutions of iron 3+ ions, which are yellow, and we've got thiocyanate ions, the SCN-, they're colourless, and when they react together we make FeSCN2+ ions, and those are red. So I am going to colour code those, yellow and red. Colourless will have to stay blank. It then says the colour of the equilibrium mixture. So once we have both of these reactions occurring at the same time, forwards reaction and backwards reaction, the colour of that mixture is orange at room temperature. So essentially we've got a mix of yellow and red, which makes it look orange. First question, again, not really reversible reactions and dynamic equilibrium sort of relevant, but it says give the name of the solvent used to dissolve the ions in this reaction. So it's a solution, so we know that we've dissolved the ions into something. The clue is in the state symbol. So anytime you see the AQ state symbol, it's not just any type of solution, it's a solution made when we've dissolved the ions in water. AQ stands for aqueous. Aqueous, I believe, came from the Latin word aqua, and that's why we use the AQ state symbol. So the name of the solvent here, water, and it has to be the name of the solvent, so please don't write H2O. Okay, the first, thinking about the position of equilibrium Le Chatelier business question, is point 2, that says a few drops of a colourless solution containing a high concentration of thiocyanate ions, the SCN-, are added to the orange equilibrium mixture. Explain the colour change observed. So first of all, we're going to have to say what the colour change is. Second of all, we're going to have to explain why that colour change occurs. So with concentrations, it's important that we identify what concentration is being changed, which is the SCN- ions up here, and then we think about whether we're increasing the concentration or we're decreasing it. And here we are adding these SCN- ions into the orange mixture. Now, Le Chatelier said that the system will always want to oppose any change that we make upon it and take itself back to what it was before we came and interfered. In the case of concentration, if we're adding more SCN minus ions, this reversible reaction wants to try and react away those excess SCN minus ions. So if I'm saying I'm going to add another 100 ions in, the equilibrium wants to use up the extra 100 to take the concentration of SCN back to what it was before. So when we increase the concentration of a reactant, that always favours the forward reaction. So if I increase the concentration here, we are going to get the excess of those ions that we now have reacting with more of the Fe3 plus ions, and we're going to get more of the forward reaction occurring. That means two things. If the Fe3 plus ions are reacting with the SCN minus ions that we've added, we're going to be using up some of these yellow ions, and those two will join together to make more red ions. So in terms of colour, there's going to be less of the yellow ions because they're reacting with the extra of these. There's going to be more of the red ions. So in terms of our colour change, we're going to see it start off orange as a mixture, and it's going to become more red as we react away those extra ions. So that's the first thing I'm going to write. So the equilibrium mixture will change colour from orange to red. So that's going to be 1 mark for saying what the colour change is. Now we're going to have to explain why. So the equilibrium mixture will change colour from orange to red. This is because the position of equilibrium will shift to the right as increasing the concentration of SCN minus ions favours the forwards reaction that will react away, that's a good phrase to use, the extra ions. And why does it do that? Because it's wanting to oppose the change that we've made. So the final thing that we must say to oppose and rather than just saying to oppose the change, it's really good to specify what the change is. So to oppose the increased concentration of SCN minus ions in this case. Now that's a pretty standard answer that we can give at GCSE, and if you're watching this and you are an A-level student, you will still need to be able to do this as well. And again, this sort of structure to your answer will work at A-level 2. So it's thinking about which way the position of equilibrium will shift, and if we've got more of the forward reaction happening, it will shift to the right, and if we have more of the backwards reaction happening, it will shift to the left. Once you've said that, you can then say which reaction is being favoured, so the forwards reaction or the backwards reaction, and why. So it favoured the forward reaction because that's going to react away the extra ions. And then the final thing that we would always say is that that is done to oppose whatever change is happening. So in this case, the increase in concentration of those particular ions. If it was temperature, you would say to oppose the increase in temperature or the decrease in temperature, or the increase in pressure or the decrease in pressure. that sort of thing. So that can become quite a stock answer that we can write for all of our sort of reversible reactions and Le Chatelier answers. Okay. Let's have a then think about the temperature. So we're told that it's orange at room temperature. It says a water bath is set up at a temperature above room temperature. When a test tube containing the orange equilibrium mixture is placed in the water bath, the mixture becomes more yellow. So at a higher temperature, the mixture turns yellow, and we have to explain what this shows about the energy change for the forwards reaction, i.e. is the forward reaction exothermic or is the forward reaction endothermic? Now, what we need to remember for temperature is that when we increase the temperature, which is what we're doing because we are setting up a water bath that is at a temperature above room temperature, increasing the temperature always favours the endothermic reaction. And again, that comes back to Le Chatelier's principle. If we are going to make the reaction really warm, the reaction is going to try and absorb all that extra heat that we are providing it with so that the temperature goes back down to what it was before we came along and interfered. That is always going to be the case for temperature. Likewise, if we decrease the temperature, that will always favour the exothermic reaction, because if we're making it colder, it wants to release heat to warm itself back up again to what it was before. So that is a factual statement you can learn. So that's how I always have to do it. Increase in temperature favours the endothermic reaction. Then we can have a think about what that means for our reaction. So it's not the case that every forward reaction is exo and every backwards is endo. We need to make sure we're thinking specifically about the example that they've given you. Now, this is a hard question because rather than saying the forward reaction is exothermic and us having to think about the colour, we're having to do it the reverse way round. We've been told how the colour is changing, and we need to then match that to this piece of information here. So, if increase in the temperature favours the endothermic reaction and it's becoming more yellow, increase in the temperature has to be favouring the backwards reaction, because these red ions are going to break down. We're going to make more of the colourless ions and more of the yellow ions, and that's going to turn the mixture less red, more yellow. So there are going to be more yellow ions than red ions, so the orange colour will start to become yellow. If we're seeing that colour change, that backwards reaction has to be favoured. If increase in the temperature favours the endothermic reaction, the backwards reaction has to be endothermic, and thus the forwards reaction will have to be exothermic, because in every reversible reaction, one way is exo, one way is endo. So now I need to try and get that into a nice, concise answer. So explain what this shows about the energy change for the forwards reaction. So the colour change from orange to yellow shows the backwards reaction has been favoured as the position of equilibrium has shifted to the left, as increasing the temperature favours the endothermic reaction, the backwards reaction must be the endothermic one. And then making sure we're going back and answering what the question's actually asking us. It's asking about the forwards reaction. So the backwards reaction must be the endothermic one, whilst the forwards reaction is the exothermic one. Hopefully you can understand where I've got that from. As always, any questions, please feel free to leave a comment on the video, or if it feels easier, you can send me an email to missgtutoringandresources@outlook.com. I'm more than happy to assist. Okay, 10.4, explain why a change in pressure does not affect the colour of the equilibrium mixture. Now, pressure is a variable that we think of only in relation to gases. So, going back to our equation, the first thing that we said was we dissolve the ions in water to make solutions. Changing the pressure is going to have absolutely no effect because none of our reactants and products are gases, and changing the pressure only comes into play when we have an equilibrium mixture of gases. So that's why it will not affect the colour of the equilibrium mixture. So it's hard to know what to write for this for 2 marks, to be fair. None of the reactants or products are gases, and changing pressure only affects the position of equilibrium for reversible reactions involving gases. Sounds like a very straightforward answer, but you have to have that recognition that we can only do or we can only think about changes to the position of equilibrium when pressure's changed if we have gases. Pressure with solutions, not going to do anything at all. Okay. It then says that other metal ions form coloured equilibrium mixtures with the thiocyanate ions. So it was the iron ions that reacted with the SCN- ions, and these, the product ions, were red. Other metal ions will form their own coloured equilibrium mixtures. Which metal ion could form a coloured equilibrium mixture with thiocyanate ions? So coloured equilibrium mixtures, coloured ions, we need to be thinking transition metals. If we had kind of colourless or white kind of equilibrium mixture, then we'd be thinking about group 1, specifically. That's the comparison that you're asked to make in the first topic. Other non-transition metal elements will be very similar. So magnesium and aluminium, although they're not in group 1, they would also form colourless solutions, kind of white solids. So the only transition metal in that list is cobalt. And so long as you've got your periodic table, you can have a look in that central section. So we've got the 2 groups on the left, then we've got the big block in the middle, then we've got the group 3, 4, 5, 6, 7 and 0. On this side, it's that rectangle there. Those are your transition metals. So if you weren't sure, just look up the positions of the elements and you're looking for one in the rectangular bit, cobalt is on the top row, 7 elements along. Okay. Any questions, as I've already said, please don't hesitate to get in touch with me. If you are studying for GCSE and you've watched this video and you're finding it really difficult, please try not to panic. This is really, really difficult content. This is, in my opinion, the hardest thing that you will do in the GCSE. If you are watching this and you're an A-level student and you're still not sure about this, again, please let me know. Bit more pressing for you guys because it's kind of assumed knowledge at this point, and you will still get questions on this, and you're going to need to use the idea of Le Chatelier's principle in the electric potentials topic, which I imagine a lot of you in year 13 are coming on to. So if I can help in any way, please just let me know. Thanks so much for watching, guys.